This one is critically important and catches people off guard constantly. I've seen students lose points on assignments, mess up their projects, even cause problems in real jobs because of this. So pay close attention. In regular Python lists, when you slice, you get a copy. The slice is completely independent from the original list. But in Numpy, when you slice, you get what's called a view. It's still pointing to the same memory. Let me show you what I mean. I'm creating a 3 by 3 matrix called A. First row is 5, 6, 7. Second row is 8, 9, 10. Third row is 11, 12, 13. Now I write B equals A, square bracket, 1 colon, comma, 1 colon. Let's think about what this slice gives us. 1 colon for rows means starting from row index 1 to the end. Remember, we count from 0, so row index 1 is actually the second row. That means we're getting the second and third rows. 1 colon for columns means starting from column index 1 to the end, so the second and third columns. So B should be first row 9, 10, second row 12, 13. That's a 2 by 2 slice from the bottom right corner of A. Now here's where things get interesting. I'm going to change B. I write B square bracket 1 comma 1 equals 100. That changes the bottom right element of B from 13 to 100. If I print B, I see 9, 10 in the first row, 12, 100 in the second row. That's what I expected. But now watch what happens when I print A. A is now first row 5, 6, 7, second row 8, 9, 10, third row 11, 12, 100. Wait, I changed B, but A changed too. The 13 in A became 100, even though I only modified B.
Why did that happen? I thought B was a separate variable.
This is exactly the trap that catches people. B is a separate variable name, but it's not separate data. They're sharing the same memory. Let me explain what's happening under the hood. When you create A, Numpy allocates a chunk of memory and stores all 9 numbers there, 5, 6, 7, 8, 9, 10, 11, 12, 13. When you write B equals A, 1 colon, comma, 1 colon, you might expect Numpy to create a fresh copy of those 4 numbers. But it doesn't! Instead, B just points to the same memory location where A's data lives. B is like a window looking at part of A's data. Numpy does this on purpose. It's famous for efficient memory management. If you have a matrix with 1,000,000 elements and you slice out half of it, do you really want to copy 500,000 numbers? That wastes memory and takes time, so Numpy says, I'll just let you look at the original data through a different window. The problem is, when you change something through that window, when you modify B, you're actually changing the underlying memory that A also points to. So A sees the change too.
That is very interesting. Now, how do we avoid that?
Use .copy to create an independent copy. Watch this. I write B equals A, square bracket, 1 colon, comma, 1 colon, dot copy, parentheses. That dot copy at the end tells Numpy, actually, I do want you to create a fresh copy of this data. Give B its own separate chunk of memory. Now if I write B, square bracket, 1 comma 1 equals 100, only B changes. A stays exactly the same because they're no longer sharing memory. This has serious implications for real work. Imagine you load a dataset with customer information. You slice out a portion to experiment with. You make changes, run some analysis, everything looks great. But then you go back to your original dataset and discover it's been modified too. You've accidentally destroyed your original data. I've seen this happen to students. I've seen this happen to professionals. It's a sneaky bug because your code runs without any errors. Python doesn't warn you. Everything seems fine until you realize your original data is corrupted. So here's the rule. Whenever you slice a Numpy array and you plan to modify that slice, ask yourself, do I want changes to affect the original? If the answer is no, add .copy at the end. Always use .copy when you want to modify a slice independently.